Right. Intersection of two planes. There are three geometries. And here we have intersecting of a plane with another plane where the intersection is a line. So there'll be a line of intersection. Okay. The second view here to the right is a cross-sectional view. If you look at it in the cross-section, it looks like two lines crossing in two space. And very much so, right? Again, there's an infinite number of points of intersection. It's impossible to have a single point of intersection of two planes. If the two planes are parallel, it's a plane of intersection. The planes are called coincident, and there are infinite number of points of intersection in that plane. The cross-sectional view to the right looks like one line on top of the other in two space, very much so, okay? And the third geometry is parallel but distinct. Okay, and the cross section looks like two lines. They're parallel but separate. No intersection at all. So the three options are a line of intersection when the planes are not parallel, infinite number of points along that line. Coincident planes, they're parallel and they're the same plane, infinite number of points of intersection on a plane. And the third option is parallel but distinct with absolutely no points of intersection. So if you have two planes given in Cartesian equations, to find the solution, you have to find the point of intersection. So if you solve the two, you'll get the points of intersection. There'll either be no solution or there'll be an infinite number of solutions along a line or along a plane. If the planes are parallel, then normal 1 will be proportional to normal 2. If the two planes are coincident, then D1 will be the same proportion with D2 as the parallel normals will be, okay? So all four parameters will have to be proportional. So we're going to deal with them case by case. Notice we have the same diagram, but now they've added in the normals. The angle between the planes is the same as the angle between the normals. I don't think they'll be asking us for the angle at this point, but that is the case. So A, B, and C, the normals are not proportional. Okay, so normal 1 is not a proportion of normal 2. By solving the system, you'll be able to find two of the variables in terms of the third. There's an infinite number of solutions. And here's a key thing. The cross product of the two normals gives you the direction vector of the line of intersection. Okay, let's go to the first example. Find the points of intersection of the following two planes. Give a geometric representation of the solution. All right, so the first thing is plane 1 parallel to plane 2. We have to answer that question. So, -2, 3, and 1 is proportional to 3, -1, and 2. Is that true? No. Normal 1 is not parallel to normal 2. And here we know there will be a line of intersection. Okay, so we've already interpreted the geometry, a geometric representation. So there's a line of intersection. We need to go ahead and solve the two equations. So to do that, I'll work over here to the right a little bit. And in the first step, I'm going to cancel or eliminate y. So eliminate y. And to do that, I'm going to take equation 1 and add 3 of equation 2. So that gives me 7x and 7z, and that's equal to plus 0 is equal to 0. So, that means x plus, sorry, that was supposed to be a z there. X plus z is equal to 0. Now I need to get the equation of a line. I know it's going to be a line. So I'm going to let x equal t, then z will have to be equal to what? Well, negative t, won't it? So there's my first two parametrics. I'm going to sub that into equation 1. Okay, and so I get negative 2 x is t plus 3y plus negative t plus 6 is equal to 0. So 3y plus 6 minus 3t is equal to 0. And y is equal to negative 2 plus t. And x is equal to t, and z is equal to negative t. I'm just writing down the parametrics I had before. There's the equation of the line of intersection. In vector form, r would be equal to 0, negative 2, 0, plus t, 1, 1, and negative 1. Now, I want to verify something. I want you to cross normal 1. So this is an aside. It's not asking for this in the question. I'd like you to cross normal 1 with normal 2 and verify that the direction vector is 1, 1, and negative 1, right? So we'll do the cross product. Negative 2, 3, 1, negative 2, 3, 1. Those are the components of normal 1. Components of normal 2. And now I'm going to do the cross product. Ignore that. That's 6 minus negative 1, so that's 7. 3 minus negative 4 is 7. And 2 minus 9 is negative 7. Oh, if I factor out a scalar of 7, I get 1, 1, and negative 1. Yeah, that's the same. So the cross product of the two normals gives you the direction vector, the line of intersection, when you have the intersection of two planes. That's sort of an aside. That was that last point from the previous slide. So we just verified this. Okay. Now on to the next case. The next case is the intersection of two planes along a plane. So the planes are identical. The normals have to be proportional, and the d-values have to follow the same proportion. Okay. Then the vectors are coincidental. So is plane 1 parallel to plane 2? 1, negative 2, and 3, proportional to negative 3, 6, and negative 9. Yes, if lambda is equal to what? Negative 1/3, then that works. Is 1 equal to negative 1/3 times negative 3? This is d1 and d2. Yes, they are equal. That is true. So, I could do it as one big set of numbers even. There's A, B, C, and D is equal to negative 1/3. I guess I could have done that in one step if you like. Okay, those are true. So plane 1 and plane 2 intersect in a plane, and you just have to state one of the equations. Coincident planes is the geometry. Okay. Parallel and distinct planes. So A, B, and C will be proportional from the normals, but D's will not. So is plane 1 parallel to plane 2? Well, let's just see. Negative 4 times 1, negative 1, negative 2 is equal to negative 4, 4, and 8. That's true. So yes, they are parallel. Is negative 4 times 1 equal to negative 3? No. So the planes are parallel and distinct with no intersection. Okay. Class of each pair of planes as distinct, coincident, or intersecting. Do not attempt to solve. Okay. 2 of normal 1 is equal to normal 2. Therefore, plane 1 is parallel to plane 2. 2 of D1 is equal to D2. Therefore, planes are coincident. Are coincident planes. Let me see. Oh, are they parallel or coincident? Let's see. 3, 6, and -9. And 2, 4, and -6. If I multiply this by 2, I get 6, 12, and -18. If I multiply this by 3, I get 6, 12, and -18. So parallel 1, plane 1 is parallel to plane 2. Now the d values is 2 times -3 equal to 3 times -4, right? This is d1 and d2. Is that true? No. So plane 1 is parallel to plane 2, but distinct. One, 2, and 3. Proportional to 3, 2, and 1. Is that true? No. Plane 1 and plane 2 are not parallel and will intersect at a line.